All right, let's talk about another kind of limit that's going to be important for us. The first kind of limit that we spoke about was derivatives, okay, which effectively finds the slope of a tangent line to a curve. Let's talk about something called integration now. Okay, so suppose that f is some function that maps real numbers to real numbers. Maybe we have something like this. Here's our x-axis down here, and maybe we have some function that takes the real numbers down here and maps them, you could say, or assigns to them values from this via this function f. Okay, so this is my function f of x. Okay, let's say I pick a couple of points, say A and B. Then the integral of the function f between 2 points A and B is simply the area bounded by the function f in the horizontal line there at y equals 0, and these vertical lines where x equals A and x equals B. That is, we want the integral to be just simply this area that's swept out. So this is really, really useful because it allows us to get, at least in theory, it allows us to obtain expressions for and sometimes even evaluate areas for strangely shaped shapes, right? Things with curvy sides. Okay. Now, don't let this. So this again is the area. Okay. Don't let this get confusing for you. The definition of this thing, it's defined to be, is what that symbol means. It's the limit of a certain sum. And here's what that sum means. First of all, if I take b minus a and divide it by n, let's let n be some number like, I don't know, in this case maybe n equals 5. Okay? 1, 2, 3, 4, 5. I'm just going to partition this interval into 5 little pieces there. If I take b minus a, that's this length, divide it by 5, or whatever n is, then that gets me this distance. Okay, so this amount here, this distance right in there, from there to there, you can think of as some change in x, which is, in this case, it's b minus a divided by n. Okay, so that's some sort of horizontal distance there. And then this part here, this is f of all this stuff. What is this? Let's see. I'm starting at A. I'm starting at the point A, and I'm adding, let's see, k of these b minus a over n things, or k of these. This is a delta x, right? This is my change in x. So if k starts with 1, then I've got 1 delta x. I'm just starting at k and going 1 delta x over. Boop. I'm finding the function f evaluated at that mark. Okay, so if I multiply this by this, that gets me the base times the height, right? Which is that area right there. Okay, and then plus, right? This is a summation. So then it says take again this same delta x, which is b minus a over n, and then multiply by this height, right? Boop. F. But this time f is evaluated at a plus 2 of these delta x's. 1, 2 of these delta x's. Okay? So you can see there that what we're doing is we're getting these rectangles in here. Okay? This is what that summation is. So all this stuff on the right, without the limit on it, is just a summation of rectangles. Rectangular areas, excuse me. Okay, and so we get something like that. The summation on the right is the area inside all those rectangles added up. Now, you might be able to sort of imagine that if n gets really large, then this delta x gets really small, and so these rectangular areas, when you add them all up, they should approximate the area bounded by the curve. And in fact, that's what the fundamental theorem of calculus says. It says that if little f and big F are continuous functions on some interval a to b, and if the derivative of big F with respect to x is this other function, little f, for every x in that interval, then it turns out the integral of f of x with respect to x, little f of x with respect to x, is in fact just the big F function evaluated at B minus the big F function evaluated at A. Okay? So, by the way, you want to be able to think about, now this is actually sort of a, we're not going to prove this by any means. You can find more information about this result in a calculus text, but I do want to point out that the way that you want to see this integral is, think of this as like, okay, so here is the height of a function, and here is some little dx or delta x. Okay, so height times width, that gives you the area of a rectangle, right? So if this dx is really, really small, then you've got a really, really small rectangle. And this integral sign, it looks sort of like an S, right? For sum, S for sum. Okay, so it sort of says sum up all of these rectangles and so forth. It's really expressed as this, you can think of it as a limit of this summation. But it sort of indicates that we're doing things continuously. Okay, we're taking the limit of this, and we're evaluating between A and B. Okay, so great. So let's try a few. You know what? So how would I integrate this? Well, the fundamental theorem of calculus says that. Okay, let's see. Maybe if this stuff in here, f of x equals 2e to the negative 2x. Let's let that be my little function f. The fundamental theorem of calculus says is that if I can find some other function, big F, such that the derivative of it with respect to x is this function, then I can evaluate this integral by doing this. Okay. In fact, I think I can, because you know what? I know how to take the derivative of stuff that looks like e to the stuff, right? So I just need to go backwards. I need to, okay, so I'm going to extend this equal sign out here. This is where I'm going to do this thing. If I had e to the negative 2x, and if I differentiated it, what would the derivative look like? It would be the same stuff, but then I'd have to take the derivative of this stuff and drop it down here. I get a negative 2 e to the negative 2x. That's not exactly what I want, because that would it's almost there, but because it gets me the 2 there, but not the minus sign. So actually, there we go. I'll drop put the minus sign there. Okay. Now you can see that if in fact if I differentiated this thing with respect to x, I would get negative 2, which is positive 2, e to the negative 2x. Okay. Good. So what I'm going to do is this is just shorthand notation for evaluating this function at the two limit points. What it really means is take the, you can think of it as a limit of this as x goes to 3 minus the limit of this stuff as x goes to 1. Okay, or effectively, if you're on a closed interval like this, then you can say that this will be negative e to the negative 2 times 3, right? F of b, this is this upper limit point, minus, this is this minus sign, okay, negative e to the negative 2 times 1. Okay, so I'm just for practical purposes, I'm subbing in those limit points. Okay, so should probably put that in parentheses there. That turns out to be what, e to the negative 2 minus e to the negative 6. And with your calculator, you can find that to be, that's approximately 0.135335. Okay, goes on and on. Okay. All right, what about this next one? Here I've got a constant that I don't know. It's lambda. Okay, it's lambda, and it appears in both places. So hey, you know what? This integrand is really just sort of, it's a lot like this, right? My limits are different. Okay, so instead of 2's here, we have lambdas, and instead of the lower limit being 1 and upper limit being 3, we're going from 0 to infinity. Let's graph this function, by the way, just to take a look at it, this function is actually kind of important to us. This function sitting in here is actually the probability density function for a exponential random variable with parameter lambda, which we may encounter in this course. So what happens when x is equal to 0? When x equals 0, then this integrand here is just it's just lambda, right? So this is lambda. So when I integrate this function, this is the function, by the way, just lambda e to the negative lambda x. When I integrate this function, what I'm actually asking for here then is the total area bounded by that curve and the x-axis from the y-axis going all the way out to infinity. Okay, so I can do this similarly as the one previous. Pull that funny equal sign out like that. This will be negative e to the negative lambda x from 0 to infinity, right? I can check that. I always double check it by differentiating by differentiating this function and make sure that I get back my original function in the integrand. If I differentiate this, I'd get all the same stuff, right? But then multiply by the derivative of what appears up here. That's in the chain rule, right? Due to the chain rule. So the derivative of all this stuff is negative lambda, and that would certainly get me that. So this, you actually want to think of that this is sort of a limit. As x goes to infinity, what happens to all of this as x goes to infinity? As x goes to infinity, all of this stuff gets really, really big. Negative, really, really big. This goes to negative infinity. E to the negative infinity. If I take e to a negative, very large negative number, this is going to 0. And then minus, from this minus sign here, minus negative e to the negative lambda times 0, right? So this is 0 times this. This is 0 on the top. E to the 0 is 1. You get negative, negative 1. All of this evaluates to 1. Okay? Let's do one more. Here's a polynomial for us. We know how to differentiate polynomials. That means we should know how to integrate polynomials too. Okay? So let's see. So how does this look for us? So let's see. How I need to come up with a function that if I differentiated it, I would get this stuff back, right? Well, remember how you take a derivative of a polynomial. You take the power and drop it down to the side, right? And then go back up to the power and subtract 1 from it, right? So let's go in reverse. I'm gonna say this is x raised to the 4th, right? I'm gonna raise that up to the 4th, and now I need to divide by 4, right? That's because, you know, I can check this now to get this term back. If I drop the exponent down to the side, it would cancel with the 4, and then I'd drop take a 1 off of the exponent there, and I'd get the 3 there. Okay. What about the next term? I'm going to take x raised to the 3rd, because I'm going to increase that 2 by 1, and then divide by 3, right? And again, I can check this, because if I differentiated this term, I would take this number down, which would cancel with the 3 down there, and drop this by 1, and I would have x squared. Okay? Yeah. All right. So, and that's going from 0 to 3. And let's see, what does that evaluate to? That's going to be 3 to the 4th over 4 minus 5 times 0 to the 3rd over 3. And then minus, right? Minus, I'm going to evaluate this stuff now at the other endpoint, which is 0. Maybe I'll put all this in parentheses there. 0 to the 4th over 4 minus 5 times 0 to the 3rd over 3. I've made a mistake, haven't I? Yes, sorry about that. This 0 should be a 3. Yeah, sorry about that, because I'm evaluating at 3, this function at 3 first. Okay, see that? So I have 3's in there. Okay, now all of this stuff, of course, evaluates to 0, and you can check that this stuff actually comes out to be negative 24.75. Okay, that is, the area is negative. The area is negative. Holy smokes! Is that okay? I don't know. Let's graph this function to see what does that indicate. How can you have negative area? Well, let's see. Negative 10, negative 20. You can use a graphing program to do this. You don't have to do it by hand, but maybe this is 2. This is we have 2, 4, 6, 8, something like that. If you graph this function, you should see that it's sort of, see, it's going to cross here at 5, I guess, and you should see that it sort of goes like this. Okay. And we're integrating this guy from 0 to 3. From 0 up to 3. Here's 3. Okay. So it's, remember, when you integrate, you're finding the area bounded by the curve in the x-axis. So yeah, in fact, so that sort of makes sense. What this means then is that if this function, which, here's the function, this is the function x cubed, this is the function called x cubed minus 5x squared. Okay, if this function drops below 0 and you integrate it in that region, then the area is going to be negative. Okay, so it's okay to have negative areas. That's just what it means. It means that the curve is below the x-axis there.